Hello all. We got a pretty long question, so I'm just going to dive right in. The statement reads, a conducting sphere of potential V naught is half embedded in linear dielectric material of susceptibility chi-e, which occupies the region z less than 0. Claim, the potential everywhere is exactly the same as it would have been in the absence of the dielectric. Check the claim as follows. A. Write down the formula for the proposed potential V of R in terms of V naught, capital R, and little r. Use it to determine the field, the polarization, the bound charge, and the free charge distribution on the sphere. B. Show that the resulting charge configuration would indeed produce the potential VR. C. Appeal to the uniqueness theorem to complete the argument. D. Could you solve this configuration in the second diagram with the same potential? If not, explain why. So let's go take a look at our diagrams. So the first one, we see that we have V naught on the spherical shell of radius big R, and it is indeed half embedded in a dielectric, the gray stuff, and it's, again, half embedded, which is important, as compared to the next diagrams A and B, where we see that we have a similar scenario on A, just it's more embedded, it's beyond half, and B, we have a weird 3/4 of embedding. Alright, so our solution for part A. The proposed potential would look something like V of R is equal to V naught times capital R over little r. Again, we would expect that decay to happen so that the boundary condition at infinity would equal 0 is met. So then we just take the negative gradient, we find the electric field. From the electric field, we can find the polarization. I'll just plug that into epsilon naught chi-e times E. Moving forward, let's note that this is all, again, in the region of z less than 0. Since there's no dielectric material above z equals 0, P is equal to 0 above it. So then we can just calculate the bound charge with P dot with n hat. Here n hat is just negative R, so that's how we get the negative in there. If V is to have the requirements of this spherical symmetry, the charge must be uniform, so we spread that charge out throughout the whole sphere. So that's why we have sigma total equal 4 pi r squared is equal to q total, which is equal to 4 pi epsilon naught r times v naught. So now we can just write v naught, or write sigma in terms of v naught. Solving through, we have on the northern hemisphere, where there is no dielectric, epsilon naught v naught over r. Where there is dielectric on the southern hemisphere, we have epsilon naught v naught over r times 1 plus the susceptibility chi-e. That was a mess, but it all makes sense when you reason it out. For B, by this construction, we know that the total surface charge is equal to the bound charge plus the free charge, which is all equal to epsilon naught v naught divided by r. And we know that this is uniform. On the northern hemisphere, we see that the bound charge sigma b is equal to 0. Thus, the free charge is equal to epsilon naught v naught over r. On the southern, we have that bound charge negative, as we found in part A. And so, therefore, the free charge is equal to epsilon v naught over r. Again, note that the epsilon there is equal to epsilon naught 1 plus chi-e, and that's where we get the cancellations to ensure that the total is still equal to epsilon naught v naught over r. So the potential of the uniformly charged sphere is v naught equal q total over 4 pi epsilon naught r. We know that q total is sigma total times the surface area. We get a host of cancellations. Q total, as we know, is, as stated above, is epsilon naught v naught over r. The r's cancel, the epsilon naughts cancel, leaving us with the proposed potential. So for part C, since everything is consistent and the boundary conditions V equal V naught at the surface R equal little r equal capital R, and also that V goes to 0 at infinity, which is why we set up the reciprocal relationship. Since those are met, the uniqueness theorem then guarantees that this is the solution. Moving on to part D, we note that for figure B in the second diagram setup, we could maneuver the same way as we did for this diagram setup, simply due to symmetry. Figure A doesn't work because this thing is more than halfway embedded and there is no symmetry. Therefore, P is not perpendicular to the in-hat or the radial direction. So we would get a bound charge on the surface, spoiling the symmetry.